Today we're going to start walking through Earth history, beginning all the way at the formation of the planet and, well, going to about 2.5 billion years ago. So we're going to be going through several billion years of Earth's history here. So this is a time period known as the Precambrian. The Precambrian makes up about 87% of Earth's history. It's broken into three major time periods. The Hadean, which you can see is from the formation of Earth to about 4 billion years ago. The Archaean, which is 4 billion to 2.5 billion, and then the Proterozoic. Today we're not going to talk about the Proterozoic, we're going to focus on the Hadean and the Archaean. And that brings us back to this geologic timescale. Remember, Earth formed here. Here's today. All of these fit into here, and all of these fit into here. And this is to scale. So the bigger the box, the longer the time period. Today, we're just going to be focusing on these two time periods, the Hadean and the Archaean. Well, if we're going to do that, we need to start all the way back when the Earth formed. And the Earth formed when our solar system formed. Now, the origin of our solar system, you might have gone over this in physical geology, but just in case you didn't, I want to make sure we all know where the planet came from. The way we got our solar system is described by the nebular theory. And, well, this starts with a nebula. Not that nebula. I think she kicked my ass. How about a nebula like this? This is part of the Eagle Nebula. And a nebula is this cloud of gas and dust off in space. And what happens is you have this cloud of gas and dust in space that starts contracting. And it contracts under the force of gravity. Basically anything with mass is attracted to anything else with mass, and so it starts pulling together. And it contracts into this rotating disk. So you have this kind of spinning disk. And then this says dust accretes into larger masses. Well, accrete means that these particles would hit each other and stick together, slowly growing bigger and bigger. And eventually they grow big enough that we have almost like the beginnings of planets, which are called planetesimals. And here towards the inner part of the solar system, rocky planetesimals come together. And that's because the minerals that make up the rocky planets are stable closer to the center where it's a lot hotter. Here in the outside part of this disk, the gas-rich planets start accumulating, start accreting. And that's because farther away from the center where it's colder, the gases are more stable. So anyway, we have these collisions continue for a while, building bigger and bigger and bigger planets. Let's see. We have the solar wind from the protostar clears remnant gases from the nebula. Eventually, the sun has fusion starting in it. And fusion is a reaction where two atoms will come together to make one atom. In the case of our sun, two hydrogens come together to make a helium. And when those two hydrogens come together making helium, it gives off the energy, the light, and the heat that we feel. And so ultimately we end up with our solar system where we have the sun, our star, in the middle, and we have all of the planets orbiting that. All right. Now early on when this was happening, right? Pretty much right when we have the planets come together and fusion start and the sun and that kind of stuff, Earth is of course forming. And it begins as a homogeneous irregular mass. Homogeneous means it had exactly the same composition throughout the whole planetary body. You could be here in the middle and it would be the same composition as around the edges. But it was hot. And that made it molten, it made it liquid. And thus, gravity could shape it into a sphere. Because basically the whole planet was pulled in towards itself, towards its center of mass, which shaped it into a sphere. But in addition to that, since it was molten, differentiation could occur. Differentiation is where heavy material sank to the center of the planet to become the very dense core that we have. The lighter material floated out towards the edge, becoming the low-density crust of the Earth. And then while this was going on, this event happened. A Mars-sized object struck Earth. What did this do? Well, when it hit Earth, the giant impact quickly propelled a shower of debris into space around our planet. So for a while, Earth actually had a ring around it, kind of like Saturn, this ring of debris from that. Now this impact also tilted Earth's axis. So instead of being straight up and down, it got tilted slightly, and it sped up Earth's rotation. So the rotation sped up, it tilted the axis, we had this ring of debris around our planet, but that ring of debris ended up coalescing, it ended up coming together and creating the moon that we have today. So now we have an Earth and we have a moon. Alright, so now we can begin the Hadean. And I wrote that this is an informal unit of geologic time. So for a time period to get a formal name, there's all kinds of things that you have to do. There's, in fact, like a commission on stratigraphic nomenclature and all kinds of stuff that has to be approved. And this has not gone through all of that approval, but pretty much every geologist calls it this. So even though it's informal, everyone knows what you mean if you say Hadean. Hadean goes from the formation of the Earth to 4.0 billion years ago, and there's very few rocks that survive from this time, because this time was, well, just not very hospitable. You can see this is an artist's rendition of this time period. The moon was actually a lot closer to Earth. That's why it looks so big there. And we had this like magma ocean with just a few early blocks of solidified rock in it. This is another artist's rendition. There's our few solidified blocks in the magma ocean and the giant moon there. So there's not a lot that survives from this time. What do we have from the Hadean? We have some meteorites. We have some mineral grains called zircon. Zircons are a very durable type of mineral. And they're in the sedimentary rocks of the Jack Hills. These are Jack Hills off in Western Australia. In those sedimentary rocks, a few of those sand grains are these zircons, these very hardy minerals that have survived all the way from 4.36 billion years ago. So those rocks are not from that time, but some of the little sand grains inside are. And then we have the Nouveau-Guatuic greenstone in Quebec that has tentatively been dated to 4.28 billion years old. A little bit of debate on that, but possibly those are from the Hadean, possibly. And then we have the Acosta Nice, which we see right there. And the Acosta Nice is in the Northwest Territory in Canada. It has been dated to 4.03 billion years old, so it is just Hadean. It's almost at that kind of, you could think of this as being from the Hadean Archaean boundary. So we really don't have a lot of rocks from this incredibly inhospitable Hadean times. But what can we infer from what we have of the Hadean? What can we figure out this time period was like? Well, I said it has this magma ocean and a special type of rock, a special type of igneous rock called komatiites form from this magma ocean. These are ultramafic lavas. This is what a komatiite looks like. This is a special texture typical of a komatiite called a spinifex texture. Now, these ultramafic komatiites do not erupt today. We don't have them anymore. And the reason is early Earth was hotter than it is today. In order to get an ultramafic lava flow, you need a lot of heat. And we just don't have enough in Earth anymore to create these. So those things were some early crustal rocks that ended up forming. Now, by about 4.36 billion years ago, we must have had small bits of continental crust. Now, first of all, why do I say this age? Remember those zircons in the Jack Hills? Well, zircons form when you have granites forming. That's a mineral that forms in granites. So if we have zircons, we know we must have had granites forming at that time. Or at least granitic, meaning kind of that composition. So how do we get continental granitic crust forming? Well, this is more felsic, and you get that from partial melting. Think back to physical geology when you were taught like Bowens reaction series and that different minerals will melt or will cool at different temperatures. Well, those mafic minerals and ultramafic minerals have very high melting points. Your felsic minerals have lower melting points. So what happens is if you have a whole mix of different minerals and different elements, and you start to melt it, well, the low temperature stuff will melt and the high temperature stuff will get left behind. So you end up with this residue, which we call the restite, and then you get your felsic magma from that. And so this should look familiar from physical geology. Bowens reaction series. Down here is the lowest melting point. Up here is the highest. Right? That's what we're looking at with temperature regimes. So as we start to raise the temperature, these minerals will melt, these will not. Raise it a little more, these minerals will melt, these will not. And that's how we get more felsic material, is from this partial melting. So eventually we start getting our different crusts forming. We have the more mafic material and we have the more felsic granitic continental material. Now, what about the Archean atmosphere? So we're going to leave the Hadean. We're going to talk a bit more about the Archean now. And prior to 3.8 billion years ago, there was absolutely no free oxygen. And when I talk about free oxygen, we're talking about O2, the molecular stuff you and I breathe in order to survive. None of this was in the atmosphere. The atmosphere is actually a mix of carbon dioxide, nitrogen, and other gases. And where did these gases come from? Well, probably meteorites and comets that hit the planet. So there was this time period in the late Hadean, early Archean called the late heavy bombardment, where a whole lot of meteorites and comets hit the planet and brought with them some of these gases and probably also water. And where else did we get these gases from? Outgassing. Water vapor and some other gases were also expelled from rock. Again, remember from physical geology, when volcanoes erupt, there's always dissolved gases in the magma. Well, it was the same back at this point in time. There were gases dissolved in there, and so some of the atmosphere and water would come out of this outgassing from the rock as it would solidify. Most of this outgassing occurred within about the first billion years of Earth's history. Eventually, water vapor condensed into rain, and of course rain would fall, it would gather in the lowest areas, just like it does today, and eventually would create our oceans. And oceans did exist by about 3.8 billion years ago, and this is based on the earliest marine sedimentary rocks that have been found. Let's look a little more at the ocean. So the ocean only really developed once everything on Earth cooled enough so liquid water could condense. So we're not talking early Hadean, right, when we had a magma ocean. So if things had to cool down enough that liquid water would condense and fall as precipitation and accumulate. And by about 4.4 billion years ago, we probably had some localized areas where water was accumulating. Now, due to high carbon dioxide in the atmosphere at the time, these oceans were really acidic. And this is because the more carbon dioxide you have in the atmosphere, the more of it can dissolve in water, and the more that gets dissolved in water, the more carbonic acid you get in water. So you ended up having very acidic oceans early on. But chemical weathering of some of the early rocks on the planet added ions, basically added chemicals to the oceans that helped buffer this acidity, helped lower that. Where's all the salt in the oceans come from? Well, again, we have weathering of the land, and material gets dissolved into water that flows off the land and into the ocean, and some of that material that's dissolved is salt. Now, when water then evaporates, salt is left behind. So you'd have these early rivers carrying dissolved salt to the oceans, and the water would evaporate, leave salt behind. More rivers would bring salt in there, water would evaporate, leave salt behind, eventually building up some salinity in the world's oceans. For about the last 600 million years, though, the salinity of the oceans has stayed relatively the same. Normal marine salinity is about 36 parts per thousand. And this is because even though rivers still carry salt into the oceans today, we also have places where salt is precipitating out of the oceans. And thus we seem to have this nice balance going on in the oceans these days. All right, so for life to exist on the planet, we're going to need not just those oceans to develop, but we need our atmosphere to change a little bit. At least for life like us to develop, right? We need oxygen. And so let's take a look at how oxygen got added to that early inhospitable atmosphere. Well, when I say inhospitable, to us, to other organisms, it was a fantastic place to live. All right, so life in an oxygen-rich atmosphere evolved interdependently. And when I say interdependently, that means that basically life changed the atmosphere and the atmosphere changed life. So there is this constant interaction between the two to ultimately lead to what we have today. So levels of oxygen, O2, began to rise about 2.5 to 1.8 billion years ago in this time that we call the Great Oxidation Event. So the question then would be, well, where does this oxygen suddenly come from during that time? Well, it comes from two places. One is something called photochemical dissociation. This happens up in the atmosphere. When you have incoming solar energy, it can actually break apart water molecules and things that have oxygen in it. And when it breaks those apart, the oxygens can come together as O2. This is, while it does happen, that's not the big important source of oxygen in this case. The big important source is photosynthetic organisms. You start having organisms like cyanobacteria evolve. Cyanobacteria, also called blue-green algae, are photosynthetic. And so they are happily taking that carbon dioxide out of the atmosphere and as a byproduct giving off the oxygen. So if we take a look at a time scale, here's 4 billion years ago, here's today. What we end up seeing is that oxygen is really, really low for quite some time. And then starting here about 3 billion years ago, we start getting, we call them like puffs or whiffs of oxygen. And that's probably because we start having this photosynthesis occurring. So we get a little bit showing up and then really takes off 2.5 billion years ago, and we have this great oxidation event that raises the amount of oxygen in the atmosphere significantly. And then we eventually get to where we are today, right here. So the question you might have is, how do we know this happened? Since no one was alive, how do we know there was such low oxygen back then and much higher oxygen at this time? Well, in volume 2, we're going to take a look at how we know that.